Hello everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concept of wave reflection. We will be learning about what causes refraction, the behavior of waves during refraction, how to draw refracted waves, as well as look at some of the natural phenomena of refracted waves. So, first of all, let's understand what refraction is. So, refraction is when the waves change the direction of travel due to the change in speed. So, what this statement here means is that refraction is the term given to the concept where we observe that the waves have changed direction. And the reason for the change in direction is due to the change in speed. You need to know what is the change in direction when the speed changes. When waves travel from faster to slower speed, the waves refract towards normal, whereas when the waves travel from slower to faster, the waves refract away from normal. Now, if you have already learned about light refraction, then this concept should not be new to you. Now, if this concept is rather new to you, don't worry, we'll go through this in more detail. So the diagram that you can see on the right hand side here is showing us light refraction, where a single light ray is shown towards a glass block. When light travels from air to glass, there's a change in speed. Light travels faster in air while it travels slower in glass. So what you can see here is that when light changes from air to glass, it has refracted towards the normal. The term normal here refers to an imaginary line that is perpendicular or 90 degrees to the boundary between the two media. So this line here is the normal, and you can see that when light travels from air to glass, the light ray refracts towards normal. That means the light ray is closer to normal in the glass compared to air. However, when light is traveling from glass to air, that means slower to faster. As you can see, the normal is not here, but you can see that the light ray has moved away from that imaginary normal line. So this is showing us clearly what these two statements are saying. When traveling from faster to slower, the light has refracted towards normal, whereas from slower to faster, the light ray has refracted away from normal. This behavior is observed not only in light rays but in all waves, whether they're water waves, sound waves, or electromagnetic waves. So as you can see in this diagram, these are showing us the wavefronts of general waves. If it helps, you can think of them as water waves. So these lines here are representing the wavefronts of the waves, and the line with the arrow is representing the direction of travel. As you can see, when waves travel from deep to shallow, it's actually moving from fast to slow. The direction here refracts towards normal, where this is the normal line. Whereas when moving from shallow to deep, which is from slower to faster, you can see that the direction has refracted away from normal, where this dotted line here is the normal line. If this is not so clear to you, we'll be going through this in more detail in some upcoming slides. For now though, let us discuss what causes the change in speed of waves. Now, different waves obviously have different basic characteristics. Light, sound, electromagnetic waves, even seismic waves are all different types of waves. And therefore, what influences the speed of those waves depend on their characteristics and what they're traveling through. Because all these waves are different, you cannot assume that the reason for the changes in speed of these different waves are the same. They're all obviously different depending on what kind of wave they are and what medium they're traveling through. We'll only look at light, sound, and water waves in this video lesson. So, first of all, what causes the change in speed of light? Now, light is an electromagnetic wave and does not need a medium to travel. This means that light can travel through a vacuum, and in fact, it travels the fastest in vacuum. When it travels through a medium, the light will slow down. The characteristic of the medium that causes the change in speed of light is known as the optical density. You can think of optical density as something like how the particles are arranged in such a way that they cause the light to slow down, like speed bumps for light. Now, optical density is not the same thing as density. A common mistake that a lot of students make is that they assume that density causes the change in speed. Density is the ratio of mass per unit volume. And if you think about it, it's something like comparing how objects would float or sink relative to one another. What has that got to do with the speed of light? Nothing, right? So density is actually not the factor for the change in speed of light. The correct term is optical density. So you can think of this as the density of the particles in the medium with regards to light and optics. The greater the optical density, the lesser the speed of light, because it's more difficult for light to travel through. By the way, I have included some fun memes for you to just look at how some of the natural phenomena of refraction can be observed in real life. Now, let's look at change in speed of sound. Now, unlike light, sound needs a medium to travel. It is a mechanical wave and it cannot travel through vacuum. So this means that when sound travels, it depends on the medium that it's traveling through. So any changes to the medium would cause the speed of sound to change. So what I have in this list here are just some of the possible factors to change the speed of sound, but bear in mind that there are actually more factors. For now, we'll just look at a few. One of the factors is the state of medium, meaning whether it's solid, liquid, or gas. Sound travels the fastest in solid, followed by liquid, and it's the slowest in gas. Remember that this is because that solid particles are closest to one another compared to gas particles. So when the particles are closer to one another, there's a transfer of energy that happens more quickly compared to particles that are further apart. The density of the medium is also a factor. The greater the density of medium, the lesser the speed of sound. This is because when the density is greater, it means that the particles are heavier in the same volume. So when they're heavier, it's more difficult to transfer energy from one particle to another. That's why the speed is slower. Temperature of medium is also a factor. The greater the temperature of medium, the greater the speed of sound. This is because the greater the temperature, the greater the average kinetic energy, which means that if the particles can travel faster, they can also transfer energy more quickly. Now, if you'd like to learn more about sound, please watch my video about sound waves. I will put the link in the description below. Now, let's look at the change in speed of water waves. Now, water waves are caused by the movement of water particles. So any changes to water will also obviously change the speed. There are more factors that can change the speed of water waves, but we're only going to look at 3 on this slide. The first factor is the depth of water. The greater the depth of water, the greater the speed of water waves. I'll explain more about this on the next slide. The second factor is the density of water. The greater the density of water, the lesser the speed of water waves. This is again similar to sound waves, because if the particles have greater mass in the same volume, that means they're heavier, so they will move more slowly. Temperature of water is the third factor. The greater the temperature of water, the greater the speed of water waves. Again, the reason behind this is similar to sound, because if the temperature is greater, that means the average kinetic energy of the particles is greater, so the transfer of energy would also happen more quickly. Now, although I've put 3 factors here, actually, when it comes to your syllabus, you only need to focus on depth of water. So let's go into more detail about how the depth of water can change the speed of water waves. As mentioned, the greater the depth of water, the greater the speed of water waves. So keep this in mind. When it's deeper, the water waves are faster. When it's shallower, the water waves are slower. Now, you don't need to know and explain this, but if you are curious as to why the depth can change the speed of water waves, you can think of it as how friction from the sea floor affects the surface of water. As you should know by now, friction will reduce the energy, causing the speed to slow down. So how does this apply in water waves? Friction exists between the movement of the water with the sea floor. As you can see, when it's deeper, the sea floor is further away from the surface, but when it's shallower, the sea floor is much closer to the surface. The further away the seafloor is from the surface, that means the less influence the friction has on the surface. You can think of it as, even though there's friction, by the time the friction tries to affect the surface of the water, it's too far away, the water particles have already moved away from that point where the friction has occurred. But if it's shallower, there is a quicker influence between the friction with the seafloor and the surface of the water, causing the water waves to slow down more quickly. That's why the shallower the water, the slower the speed of water. Like I said, you don't need to know and explain this, but hopefully this will help you remember how the depth of water affects the speed of the water waves. A quicker way to remember this is to look at the word shallower and observe that the word slower is already there. So just remember that when the water is shallower, it's slower. So this is what I always tell my students to help them remember how the depth of water affects the speed of water waves. This video is showing us how the waves will change direction when they change speed. The black lines are representing the wavefronts of the waves. The waves are traveling faster in the top half, in the darker green area, while they are traveling slower in the bottom half, the lighter green area. As you can see, the waves are slowing down part by part. The left side of the wave slows down first, causing them to change direction before the rest of the wave slows down. And this causes the wave to refract towards normal when they're traveling from faster to slower. So, based on the previous animation, you should be able to determine the properties of waves that undergo a change. So to help you recall, I've put a screenshot of the refracted waves here. Now, as you can see from this screenshot, the change in speed causes a change in wavelength because when the waves slow down, they change direction, forcing the wavefronts to be closer to one another. And that means, yes, there will be a change in wavelength. Now, you cannot observe frequency from this kind of animation or even in real life, but you should be aware that frequency does not change. The reason for this is because frequency is the identity of the wave. It depends on the source. So, for example, if there is a motor generating water waves, the frequency of the vibration of the motor is equal to the frequency of the water waves that are generated. And this frequency will remain constant throughout the entire lifespan of the waves. There is no reason why the frequency of the wave would change if it changes speed or undergo refraction. That's why the frequency does not change. For speed, well, refraction is due to the change in speed, so obviously the speed is going to change. And finally, for amplitude, again, you cannot observe amplitude from the top view of the waves. You'll need to look at the side view. If you're taking SPM or IGCSE, you actually do not need to know about whether the amplitude changes or not, but I'm going to include this in this video lesson just to make this lesson complete. And yes, there will be a change in amplitude. Now, how does the amplitude change? I'm going to go through a little bit of a bonus section over here, so you don't need to know this if you're taking SPM or IGCSE, but I'll just explain it anyway. So very commonly, you'll come across side view images like this, which show that the amplitude doesn't change even if the water waves are changing speed due to the different depths. Now, this is actually wrong. There will be a change in amplitude, and it's not what you think. A lot of students think that when the waves slow down, the amplitude decreases. It's actually the opposite. The amplitude of the waves increases when the depth decreases, as you can see from this side view here. So the deeper the water, the smaller the amplitude, and when it gets shallower, the wave amplitude actually increases. You can also observe this in real life. When you're in the middle of the sea, you should see that the waves are moving very, very quickly with very little amplitude. Whereas at the beach, the waves are slower and they have higher amplitude as the waves crash onto the beach. You can think of it this way. When the waves are traveling faster in the middle of the sea, the energy is spread out across the wavelength. So the waves have to travel very quickly, so the amplitude is lower. But when the waves are forced to slow down, that means that the wave fronts are closer to one another. The energy, instead of being spread horizontally, is now being spread vertically. So the energy was spread out when it's deeper, But when the wave slows down, it's forced to rise up, causing the amplitude to increase. A lot of research has been done on this, and here's an excellent image that shows how the water waves will increase in amplitude as it gets shallower. So you can see in the open ocean, the water waves are faster and the wavelengths are longer. But as it gets shallower, the amplitude is forced to increase because the wavelength has decreased. So the shallower the water, the slower the water waves, and the greater the amplitude of water waves. Now let's move on with refraction. So just to remind you that when there is no change in direction, there's actually no refraction. This slide is showing us what happens when a light ray is shown towards a glass block in such a way that the light ray is perpendicular to the boundary. When there is no change in direction, there is no refraction even though there is a change in speed. Remember that refraction refers to the phenomenon when waves change direction due to the change in speed. The reason there is no change in direction is because the ray over here is perpendicular to the boundary, meaning that it is parallel to the normal. Remember that normal is 90 degrees to the boundary. The incident angle is always measured between the light ray and a normal line. So in this situation, the incident angle is 0. So when the incident angle is 0, the refracted angle is also 0. Now, this is true not only for light rays, but for all waves. So let's say we want to observe how this would apply when it comes to water waves. Let's say these lines represent the wavefronts of water waves. So you can see that the water waves are traveling from left to right, following the direction of travel. So let's say this region represents the shallow region, so the waves are forced to slow down. Therefore, the wavelength will be shorter. And then when they get back out from that shallow region, back into the deep region, the wavelength will be greater. So whether it's water waves, sound waves, or any kind of electromagnetic wave, how you explain that there is no change in direction is because when the incident angle is 0, the refracted angle is also 0. And this is true whether it is slowing down or speeding up. Now for this video, we're going to focus on water waves. So we're going to look at how to complete the wave refraction diagram for water waves. So in this slide, you can see the top diagram here is showing us the side view of a ripple tank. Now remember that a ripple tank is basically a tray that we fill with water. How can we create different depths in a tray of water? So to create a shallow region, we just need to place something at the bottom, for example, a glass block or a perspex block, in order to create a shallower region. So we have the shallow region over here, this is the deep region, and it's the source that is generating the water waves. At the bottom here is the top view of the water waves, where these lines are representing the crests or the wavefronts of the waves. And you can see how these black wavefronts are already lined up with the crest of the waves. From the side view, they show us clearly here how the water waves were traveling from fast to slow, causing the wavelengths to decrease. So to complete this diagram, we just need to add the wavefronts that are aligned to the crest, like so. So you can see how the wavelengths are greater in the deep area and are smaller in the shallow area. So this is quite easy because there's no change in direction. But what if there is a change in direction? So let's look at how we can complete this kind of wave refraction diagram. So we have over here a shallow region made up by putting a trapezium block at the bottom of the water. And we have wavefronts traveling from deep to shallow. So what I'm going to do now is I'm going to show you step by step how we can complete this wave refraction diagram. So first thing we need to do is to draw the directional arrow for the incident waves if needed. So depending on the diagram you are given, sometimes they will just give you only the wavefronts and sometimes they'll include the directional arrow. If the diagram you're given does not have the directional arrow, you need to draw that first. So the waves are traveling from left to right. You need to draw the arrow that is perpendicular to the wavefronts, like this. In my case, I've drawn the arrow as a dotted line. You actually don't need to, but I like to draw it dotted just to make it distinctively clear from the wavefront. So draw the arrow until it touches the boundary between the deep and shallow region. Next, you need to draw the normal line where the directional arrow touches the boundary. The normal line is a line that is perpendicular or 90 degrees to the boundary. So at this point where the arrow has touched the boundary, you need to draw a line that is 90 degrees to this boundary. So this dotted line here is the normal line. Next, we need to draw the waves in a shallow area. But before we draw the wavefronts, first of all, you need to draw the refracted direction. Now, how do we draw the refracted direction? Before we start drawing the direction, first, you must recall the speed of waves. Remember that water travels slower in the shallow region, slow. So water travels faster in the deep region and slower in the shallow region. When the waves travel from deep to shallow or fast to slow, the waves are refracting towards normal. Now, how do we get the direction that's towards normal? So if you're not sure, here's what you can do. I'm going to show you, but don't draw this arrow yet. Place your ruler in such a way that it is showing a straight line from deep to shallow. So if there were no change in direction, the waves would continue to travel in this same direction. However, we know that because the boundary is at an angle here, it's going to change direction. This is the normal. So the waves need to refract towards normal, meaning that this arrow needs to be placed at a closer angle towards the normal, like so. How much closer should you place? What angle should you place? If you're taking SPM and IGCSE, you don't need to calculate the angle if you're doing this for water waves, only for light rays. So for now, as long as you make this angle smaller than this angle, it will be accepted. So remember, place your ruler straight first and then make it closer towards the normal and draw an arrow to show the wave has refracted towards normal. So now that we have the refracted direction, we will need to draw the refracted wavefronts. Remember that the wavefronts need to be perpendicular to the direction of travel. My advice is don't randomly draw the lines. There is a system to this because remember that the wave is slowing down part by part. So use the wavefronts that are touching the boundary to draw the wavefronts first before drawing the rest of the wavefronts. So at the points of these two wavefronts, draw lines that are perpendicular to the direction, like so. You can see now from these two wavefronts, this is the new wavelength in the shallow region. You can draw the rest of the wavefronts at the same wavelength. So when drawing the wavefronts, make sure that the wavelength of the waves in the shallow region are constant and the wavelength is less than that of the wavelength in the deep region. And that's how you complete the wave refraction diagram for waves that are traveling from deep to shallow. What about if the waves are traveling from shallow to deep? The steps you do are actually exactly the same. We'll go through this step by step as well. So, first of all, draw the directional arrow for the incident waves if needed. Next, draw the normal line where the directional arrow touches the boundary. And then you need to draw the refracted direction. Now, remember that when waves are traveling from shallow to deep, they're moving from slow to fast, which means that they need to refract away from normal. So again, to determine the direction, first of all, place your ruler in such a way that you get a straight line without any change in direction. And to show that the waves have refracted away from normal, you need to make this angle bigger. So this arrow needs to move away from normal, creating an angle that is larger compared to the angle in the shallow region. Based on this new direction, you need to draw the refracted wavefronts that are perpendicular to this direction. Again, don't just randomly draw the wavefronts. Use the wavefronts that are already touching the boundary to help you get the new wavefronts. So at these 2 points, complete the wavefronts by drawing them perpendicular to the direction. And then you can complete the rest of the wavefronts with the same wavelength. So again, remember that the wavelengths of the waves in the deep region must be constant and the wavelength must be greater than that compared to the waves in the shallow region, because they're traveling faster in the deep region and slower in the shallow region. And that's how you complete the wave refraction diagram. Now, let's learn about a natural occurrence of wave refraction. And this kind of question could potentially come out in SPM or IGCSE. The observation which you would need to be able to explain is why the wavefronts changes shape as they approach the shoreline. So this is a top view of the shore, where this is the middle of the sea and this is the beach. The area that is protruding into the sea is known as the cape, or sometimes known as headlands, and the area that is curved away from the sea is known as the bay. So these blue lines are representing the wavefronts, and as you can see from this diagram, in the middle of the sea, the lines are rather parallel, but as they approach the shoreline, the shape slowly changes to follow the shape of the shore. So how do we explain this? So this is the top view of the shoreline, and this is the side view, where this is the surface of the sea. Let's say this is the sea floor, which is in the middle of the sea here, and as we approach the shoreline, the depth of the sea decreases towards the surface, as you can see. So this is true whether it's from the middle of the sea to the cape or middle of the sea to the bay. But as you can see, the distance from the middle of the sea to the cape is much shorter compared to the distance from the middle of the sea to the bay. That means that although the sea floor will be decreasing in depth along the shore, they will be decreasing at different rates. For the bay, it is a greater distance, but for the cape, it's a much quicker decrease in depth. So that means that the difference in depth at different points in the sea will obviously cause the waves to have different speeds at different points, which will cause the wavefronts to also change direction. So how do we explain the changes in the wavefronts? You can use this as the explanation. So sea wavefronts tend to follow the shape of the shoreline as they get near the shore. In the middle of the sea, where the depth is almost uniform, the wavefronts tend to be plane and parallel to each other because the speed is almost uniform. The depth of the seabed decreases more quickly at the cape than at the bay. Therefore, the speed decreases more quickly at the cape than at the bay. Therefore, the wavelength becomes smaller more quickly at the cape than at the bay. This causes the wavefronts to change shape. The energy of the waves will be focused towards the cape and spread out at the bay. As you can see from the shape of the waves here, the energy is focused towards the cape, whereas at the bay, they tend to be spread out. So, because the energy of the waves is spread out at the bay area is much safer than at the cape. And that is why the bay is always used for any human activities, such as ports for ships and boats, as well as for recreational activities. For example, if you want to go swimming or surfing. The cape is never used for any human activity because the energy of the waves is much higher. Boats or ships could be caught in the ocean current and crash onto the rocks in the cape area. So that's why if you were to go on a holiday, you always find that there's a lot of bay areas where the resorts are. For example, Marina Bay Sands. You'll never hear of a cape being used for resorts. Instead, you'll always hear how capes are to be avoided. For example, Cape Horn is one of the most dangerous places in the world for ships to pass because they keep getting caught in the very strong ocean current. That means that for ships, if they want to go around that area, they have to be very far away from the cape, otherwise they'll get caught in the ocean current and could potentially crash. Here are some photos to show you the wave refraction at the beach. As you can see from this top view here, the wavefronts in this ocean are following the shoreline. They're not parallel, they're actually quite curved. This photo shows us more clearly the difference between the waves at the cape and at the bay, and you can see how the waves have changed shape to follow the shoreline. This photo also shows us how the waves are spread out at the bay and are focused towards the cape. And that's all we'll be covering for wave refraction in this video. For wave refraction in SPM and IGCSE, it's more of an overview focusing mainly on water waves. There's a lot more you do need to learn about light and sound, For example, in light, you need to learn about light refraction as well as total internal reflection in terms of the calculations. For sound, you need to learn about their properties and behavior, including a little bit about sound refraction. Now, these topics are a little bit long, so I've covered these in separate videos, which I'll put the links in the description below. For now, that is all for this video. So if you found this video to be educational and helpful, do click like and let me know how this video has helped you in your studies. If you'd like to help me keep making free educational video lessons and practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, do check out my website at physicsrocks.com. For videos on other topics you might find helpful, check out my YouTube channel and subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!